So this is basically our first lecture. I'm gonna have to take a swing at it anyways. First time doing it this way. So structures of metals. This is gonna be our first chapter, essentially, reviewing really the structure of materials and how metals are essentially how they're created from atom up. So topics. I'm gonna briefly review the periodic table of elements. Go over an understanding of atomic structure, explaining atomic bonds and their characteristics, ionic, covalent, and metallic bonding, describing the crystalline structure of metals and how they determine their properties and behaviors, examine metal structures and their arrangements of atoms within, what kinds of imperfections occur in crystal structures and how they affect, or what effects they have, and effects of crystal grain and grain boundaries, strain hardening, and anisotropy of metals. So those are the topics we're going to be reviewing. I know it's kind of bland. I mean, the overall topic that we're really going to be doing is, basically understanding atomic structure of metals, and why it's important is because it really tells us how the metal is going to act when a load's applied to that metal and that material. So this is basically one of the big things we're doing in this class, is looking at different materials and how they act with loading, which is a big basis for manufacturing and what materials to use in manufacturing. Alright, elements. So periodic tables, we have approximately 110 elements, chemical elements on the table. Oxygen, silicon make up 70% of all solid matter. And out of the 110 elements, only 8 make up 97% of all Earth's substance. And that 8 is aluminum, iron, calcium, sodium, potassium, magnesium, oxygen, and silicon. So here's a view of the periodic table, and you can see we go from, our noble gases here, which we'll talk about electrons and the valence shells and different things. We're not going to go too far into it, but kind of explains what kind of bonding we're dealing with and why there are different types of bonding. So we look at this periodic table, and interestingly enough, the way the periodic table is set up, if you look at the numbering here, we have basically the number of, in left to right, top to bottom fashion, is the least heavy to the most heavy atom. So what this means is, an atom, which we haven't really seen the slide yet, is made up of electrons, protons, and neutrons, right? So what we're looking at here is basically, as these increase, you get one more electron, right? So each one adds another electron, which means you get another proton, which means you get another neutron. So you keep on adding those is up, and as you get more and more, you get a heavier element. And these are you see the orange are alkaline metals, alkaline earth metals. So you can see we go from metals over to lanthanoids, acidoids, so basically acids and things, transition metals, porous metals, other non-metals, and noble gases. So they're set up metals, essentially, in non-metals. So looking here, actually explains, interestingly enough, the electrons that are built up as we move left to right. Also can symbolize the orbitals that we have for the electrons, where they're placed in the orbitals. So I think the next slide, yep, here we go, actually shows orbitals here. So what I'm talking about when I talk about orbitals is we have orbitals in our ring structure, and they keep on moving outward. So as you see here, we have in the first orbital, 1s orbital, we have 2 electrons. In the 2s orbital, we have another 2 electrons. Then we jump up basically to 2p, and this is how the electrons are set up and how they're understood today. So we have electrons, protons, and neutrons. And this is not to scale, obviously, but just an example of an electronic or atomic structure. Excuse me. So energy levels, basically what we were talking about there with which shell or type of orbital you're in. So we had the 1s, and basically you move up in the orbitals, and for some reason I didn't get a matching alphabet. I'm surprised this one didn't go by S, P, D, and F, G, H. Must be I'm getting something else, probably in math. Yeah, it looks like a math. But it represents what I'm trying to convey here. So we have a 1s, then we have a P, and we have the d orbital, and so on, and it builds. And the number of orbitals in the energy level basically depends on number of electrons in energy level. So we can see basically, depending on your orbital, how many total orbital electrons we have. So that's kind of the gist there, and why that's important, really. And we're not going to get too far into chemistry of it necessarily, but we want to understand bonding, and that's going to be the important thing for us in manufacturing processes. So here we have our first ions, so ionic bonding here. So we have 2 types of ionic bonding, so cation versus anion, but they're both ionic bonding. So here we have neutral atom, and basically you lose an electron, so the neutral atom, so ionic bonding, sorry, is built up of cations versus, anions. So you have 2 different types of atoms trying to bond here, and this is what we're talking about, bonding. So one atom bonds to another. So when we're talking about bonding, we get, basically one of these elements wants to bond with, say, another element. So in this case, salt, sodium chloride, right, is our table salt. What we have here is we have the number of orbital shells, so we were talking about, and we have an electron here that basically it's alone in its orbital shell, and it basically wants to essentially give up. This one is close to being full in its orbital shell, and the way I always learned it and thought about it is anything really wants to be like a noble gas. So noble gases have full orbital electron shells, so they don't necessarily want to give up or take away an electron. In this case, we have chloride, which is, going back to this, switching back and forth, but it's chloride's here, and notice how it wants to gain an electron to become like a noble gas. So noble gases are important because they're stable. So this means, they're not explosive. That's why you use helium for balloons at birthday parties and not hydrogen, right? So sodium chloride wants to gain an electron to become stable, right? Where sodium, over on this side, wants to give up an electron, again, to kind of become stable, have a full outer shell. So this gives it up, and it feels more stable, but it's still basically sharing this with the chloride. So it's bonded. So it's still the sodium's electron, but chloride's using it to be more stable. And that relationship gives you cations and anions. So cations essentially give up their electron, anions take an electron. So that's the relationship there for ions. So molecular bonding, so that's our second bonding here. Molecular bonding is basically anything that's not, I guess you can think of organic. Organic is usually going to be, well, molecular bonding. So like in this case, you have CO2, so carbon dioxide, right? Stuff we breathe out. Sugar, and you notice there is a pattern to it because there's math that goes along with it, and you may need to do that if you go through chemistry, but you know, there's less of a pattern than you would see when you see various different types of ionic and different bonding, like crystal structure, for instance. But there is molecular crystals, so you know that is possible as well. But you have glucose, so sugar, and then hydrogen, or water, H2O, right? So all example of molecular bonding. The other bonding, chemical bonds. So here we have primary bonds, ionic, covalent, and metallic are primary bonds. And we have secondary bonds, molecular bonds, like we mentioned there. So I kind of missed, I think I'm missed, or maybe it's next, where I talk about ionic, covalent, and metallic individually. Alright, so that kind of gives you an idea of, you know, what's happening at molecular level so far, right? So we have atoms bonding to atoms because they're either taking or giving up an electron, right? So we mentioned this ionic bonding. I'm not going to spend too much time on it, but this takes place between atoms that have few electrons in their valence shell and those that nearly have completely filled valence shells. So that's ionic bonding. So there's typically a really strong attraction there. Covalent bonding takes place between atoms that share electrons in their outer orbits to form molecules. So this is like our what is this? H for carbon. I'm not sure. I'm not sure about that one. Not off the top of my head, anyways. Solid typically formed by covalent bonding typically have low electrical conductivity and have high hardness. So solid typically formed by covalent bonding typically have low electrical conductivity. So low electrical conductivity means they're good insulators, right? And they have high hardness, so like a ceramic. So diamonds are formed covalently bonded carbon. So actually I think this is diamond structure. I think that's an example of diamond structure. I'd have to go back and look. Metallic bonding. So metallic bonding is metals, like we're getting into, right? One of the main things we're going to be talking about in this lecture. So metallic bonding tend to have elements whose valence shell have only a few electrons. So when large numbers of atoms are combined, their valence electrons form this cloud. So you have a bunch of electrons floating all over the place, right? You can think of it that way. Anyways, that's how I kind of think of it. And it wants to reach this equilibrium, right? So it's trying to get, I think it's always 8 electrons in its valence shell, right? So it's trying to be at this equilibrium. So what's happening there is all those atoms are kind of sharing their electrons and they're just kind of floating around. And this is why they say that, you know, electron clouds allow electrons to pass really freely through them. So this is why they're really easy to conduct electricity, for instance. So you hook it to, say, an iron bar, you can electrify that bar rather easily. Whereas you hook it to like a piece of wood, you know, it's not gonna travel as easily, right? So these electron clouds result in generally a high thermal and electrical conductivity. So easy to transfer heat to. secondary bonding. So secondary bonding is typically molecular bonding to that form chain-like patterns. So this is something you see in plastic, wood, and many other materials. These tend to have low melting points, low strength, and are poor conductors of heat and electricity. So here we have just water. So secondary bonding is really the bonding between, you know, the molecules there to form the water, the wood patterns, and the plastic. Right. So typically, you know, like for instance, boiling water separates water, hydrogen and oxygen from each other rather easily, right? Pretty easy to break up that bond. So it's a form of secondary bonding, and that it's seen as a weaker bond. So solid material structures. So crystalline solids have ordered 3D geometric patterns that repeat throughout the material. Amorphous solids have no repeating 3D geometric patterns, so there is no definite form. So where I'm moving here is basically from that bonding, what kind of structure, solid structure would you get, you know, as you get to the larger and larger structure, right, from atom up, right? So what is metal made of? You know, this is what we're basically getting to, right? So typically metals are at the atomic level are derived as small cubic crystalline structures. So you can kind of see, we were talking about the bonding and everything. These are all, say, an atom of, what is this? What does it say? Let's say example like steel, for instance. Well, steel may be a bad example because that's an alloy. So iron or aluminum or something like that. So say aluminum. I think that would be a good example here because I think it's a face-centered cubic. We'll learn that here in a minute. But here we have a cube, and these are atoms of, say, aluminum, right? And they're sharing their electrons to get those, say, 8 electrons. So what we see here is there's a pattern of where they want to float, right? And so they end up building this crystal. So this crystal builds out until it hits another crystal that's built. And at the atomic level, this is actually what, say, aluminum would look like, or a metal would look like. It has a crystalline structure, and these are all representing atoms that are all sharing bonds. So basic crystal structures of metals. There are 3 basic types of atomic arrangements in metals. I said basic because these are the main types. There are some others that we won't really go over in this class. Well, the 3 are bodied center cubic, BCC, and some examples of this are alpha iron, chromium, molybdenum, tantalum, so on. Won't say all of them. Face center cubic, FCC is typically the acronym for that. So gamma iron, aluminum, copper, nickel, lead, silver, gold, platinum. So some of the common things you might see. So aluminum, is the face center cubic like we just saw. So that would be, you got an atom. The way I think of it is you got an atom on the face of your cube. So it's face-centered cubic. And then hexagonal closed packed, HCP, is beryllium, cadmium, cobalt, and so on. So that different electrical pattern, basically atomic pattern structure that you ended up getting. So BCC is, I think, one of the simplest. So bodied center cubic, we have an atom right at the center of the body, hence bodied center cubic, right? So that's our BCC structure. And basically what you get from this is atoms would arrange like this, and they would then create a pattern in that crystal structure. Face center cubic. So like I showed before, you have an atom at the center of each face, and that again gets set into a pattern that again fills out and creates a crystal. Hexagonal closed packed HCP. So it has a little bit different structure, and that's why they call it hexagonal. And they call it closed packed because it really ends up packing in quite tightly, with being able to fit these 3 extra atoms in there, along with top and bottom there. So you get a pretty tight pack of atoms for those structures. So they end up being dense. Rather dense. Alright, deforming metals. So one of the big things we're really looking at, and what's important to manufacturing, is understanding how metals deform, right? So how do we machine them? How do we mold them into what we want them to be? So understanding elastic deformation is reversible since the material yields. So what we talk about elasticity, right? Thinking about elastomers or rubber bands, they always want to return to their original state. So we have 2 different types of deformations. We have elastic deformation, we have plastic deformation. Right? You can think of plastic, right? You stretch plastic enough, eventually it's going to stretch and it's not going to go back to its original shape. But if you elastically deform something, let it go, it's going to snap back to the original shape, right? So there's two types of deformation metals go through. And here's a plot that we use for basically assessing metals. How much is it going to stretch before it actually starts yielding, essentially? So we actually intentionally stretch the metal, and where does it actually yield? Where does it go to plastic deformation, right? So that's what's really important about metal structures. And right here is an example of what's happening at the atomic level. So here we have the atoms essentially ripping apart and then reforming bonds next to them. So as long as those don't start, say, shifting atoms, right? So this one, say here, going to the next one, and so on. As long as we don't start shifting atoms, we haven't plastically deformed, essentially, is the idea there. And we'll talk a little bit more about this. This is a stress strain curve, so we will actually look at those quite a bit. So it's good to get, I guess, a little bit used to those. And one of our probably first assignments for homework is I have to actually develop those, since due to bookstore issues we might have different versions. So I might have to make up my own questions for these. That'll come later. Back to slideshow. So permanent deformation of a single crystal under a tensile load. So here, this is an example of a tensile test. So I showed you guys the tensile testers this past week, or you'll be seeing them here tomorrow, almost today here. So at this point, what we're looking at then in the metals is where does this shifting start happening? Where does the slip, what's called a slip plane, because they slip along a plane, right? So when does this start happening, under what load? And this is where we can test out, well, how much is an aluminum piece going to hold over, say, a steel piece of metal. Alright, why do dislocations increase strength? So what happens, and as we see, we have all this atomic structure, metal creates crystals, right? Well, at certain points, you end up getting a dislocation in your crystal, an imperfection, right? So why do these dislocations increase strength? Well, what's happening here is there's a missing electron, right? And if you take a positive magnet and try to move it past another positive magnet, it's hard to move, right? It has this repelling action. So what's happening here is it's basically a resistance to change, right? So the more dislocations and different things you have in your slip plane, the less likely you're actually going to have it slip along that plane. The more you have tends to make things more brittle. So the more central dislocations you have in a piece of metal tends to get brittle, but it has a really high puncture resistance. So you can't really puncture it very well, but once you kind of hit that strength, it kind of shatters or cracks, right? So that's an example of why dislocations increase strength in metals. And here's an example here from your book of single crystal slip planes. So along those slip planes, this is where that shifting starts. And you can see in this image, the nice thing about this image, why I included it, is those slip planes are going to shift along a different, axis in different planes. So this is why you rip metal apart and it looks jagged, right? Well, it's because it's not necessarily happening always along the same slip plane. In another adjacent crystal, there could be a different type of slip plane there, and this tends to be what constitutes, depending on what break you do, what kind of break, what kind of rupture and different things you have in the metal. But typically you would see that jaggedness, especially if you look up under a microscope. It'd be like a mountainous region or something. We'll see some actual images of that soon, actually. Alright, so I'm gonna pause here and we're gonna restart in another video. So I just want to chunk up the videos so they're not super long. So I'll start up with hot worked versus cold worked. What really does that mean? What are those processes, right? And what does that do to the metal? So that changes different metal properties. So I'll start back up in the next video with hot worked versus cold worked. Alright, see you in the next video.